Welcome to an alternate approach to the challenge problem. So, for example, let's evaluate the indefinite integral, which is the integral of, in the numerator, 2x cubed plus 11x squared plus 21x minus 15, all over the denominator, x squared plus 6x plus 13 dx. So recall, or note, this is actually the problem from the previous video. So now this is the same problem. As in the previous video. So as in section 6.1, part 10. We're just going to do it in a slightly different way. Right? So now we'll take a slightly different approach. So we will start off in the same way. So recall, we started with long division. To reduce the order of our numerator. So we will just go ahead and redo that long division. So on the outside, we have our x squared plus 6x plus 13. On the inside, we have 2x cubed plus 11x squared plus 21x minus 15. So 2x cubed plus 11x squared plus 21x minus 15. We run through our long division. X squared goes into 2x cubed, 2x times. Do our multiplication, we will have a 2x cubed plus 12x squared plus 26x. Then we do subtract that whole line off, and we wind up with negative x squared minus 5x. Hold down that minus 15. And again, x squared goes into negative x squared minus 1 times. Negative 1 times x squared is negative x squared. Negative 1 times 6 is a minus 6x. And then we also have a minus 13. Do our subtraction one more time. Negative x squared minus negative x squared cancels out. Negative 5x minus a negative 6x becomes a positive x. Negative 15 minus negative 13 becomes minus 2. And so we wind up with 2x minus 1 plus our new numerator is x minus 2 all over our x squared plus 6x plus 13. So this should look exactly the same as what we did in the previous video. So from here we have therefore that our integral of 2x cubed plus 11x squared plus 21x minus 15 all over x squared plus 6x plus 13 dx. This is equivalent to the integral of 2x minus 1 plus, then our fraction, the numerator, x minus 2, all over the denominator, x squared plus 6x plus 13 dx. We'll go ahead and split this as the integral of 2x minus 1 dx plus the integral of x minus 2 over x squared plus 6x plus 13 dx. Now, in the previous video, we split that fraction into a component that perfectly fit basic u substitution. And then in the second component, we just had a constant, and we forced ourselves into a tan inverse format. In this video, we're going to do our u substitution first. So again, this time we're going to change up the order. We're going to complete the square and apply u substitution first. So we are now going to complete the square. And apply u substitution. Before we split the fraction. So x squared plus 6x plus 13. Again, we want to rewrite this as x squared plus 6x plus blank. And we have our plus 13 minus blank. Completing the square, we divide that. Since there's just a 1 in front of the x squared, we just divide by 2 and then square it. So we're just adding 9 and subtracting 9. This is the exact same complete the square from previous video. So this becomes x plus 3 squared, and then 13 minus 9 is 4. So our denominator becomes x plus 3 squared plus 4. So our integral, we are looking at the integral of 2x minus 1 dx plus the integral of x plus 3 squared plus 4 is our denominator, and our numerator is still x minus 2, and then we have dx. Angle of x minus 2 over, in parentheses, x plus 3 squared, and then plus 4. Focusing on this second integral, the first one we definitely know how to solve. For the second integral, let's go ahead and simplify that problem. Let's do our u equals x plus 3. Then we have du is dx. We also have u equaling x plus 3, means that x is u minus 3. And so this integral over here becomes the integral of x is u minus 3. So we have u minus 3 and then minus 2 divided by u squared plus 4 dx, or integral, sorry, u squared plus 4 and then du, or the integral of u minus 5 over u squared plus 4 du. I keep writing dx. Of course, we also have our other components still. So we still have our integral of 2x minus 1 dx added out front. That integral, of course, we know, integral of 2x minus 1 will go to x squared minus x plus a c1, and then we have plus an integral of u minus 5 over u squared plus 4 du. At this point, we can split this as an integral of u over u squared plus 2 or plus 4 du minus 5 times the integral of 1 over u squared plus 4 du. So we are looking at x squared minus x plus c1 plus the integral of u over u squared plus 4 du minus 5 times the integral of 1 over u squared plus 4 du. This integral u over u squared plus 4 du again lends itself towards u substitution. This time around, let's go ahead and set v equal to u squared plus 4. Then we get that our dv is 2u du, or u du is 1/2 times dv. So this integral here, we can just run u substitution on. This time around, it's v substitution. So our next line, we would have x squared minus x plus c1 plus the integral of that u du becomes 1/2 dv. So we have 1 over v times 1/2 dv. Then we have minus 5 times the integral of 1 over u squared plus 2 squared du. This last integral is our perfect inverse tangent case with a equals 2. So we know that integral. Our middle integral, of course, is a natural log. So at this point, we know all of our integrals. So we have x squared minus x plus c1, then plus 1/2 times the natural log of the absolute value of v plus c2. Then we have minus 5 times 1 over 2 times tan inverse of u over 2 plus c3. Again, that's the variation of tan inverse where we have a plus a squared. Now we can go ahead and combine all our c's together. So if we set c equal to c1 plus c2 plus c3, we can jump straight there. If you want to ignore the c's until the very end, that is perfectly fine. You can find an antiderivative and then just add c at the end. So we have x squared minus x plus 1/2 times the natural log of the absolute value of v minus 5/2 times tan inverse of u over 2 and then plus c at the end. Now v was equal to u squared plus 4. So we can go ahead and plug in our v. And we have x squared minus x plus 1/2 times the natural log of the absolute value of u squared plus 4 minus 5/2 times tan inverse of u over 2, all plus c. And here our u was x plus 3. So we can go ahead and plug that in, and we are looking at x squared minus x plus 1/2 times the natural log of the absolute value of x plus 3 squared plus 4 minus 5/2 tan inverse of x plus 3 over 2, and then plus c. So again, this gets us the same answer as we had previously. This is just an alternate approach that we can take for finding the integral. Either one is perfectly acceptable. Plenty of integrals we take in this class. There will be numerous ways that you can get to the answer, especially as the integrals get more complicated.